section, we're going to overview the network core. We're going to see what happens inside the network core, and we're going to introduce a number of important topics. We'll talk about packet forwarding, packet queuing delays, and packet loss. We'll talk about an alternative to packet switching known as circuit switching, and we'll talk about the structure of the internet. We'll see what we mean when we say the internet is a network of networks. The network core consists simply of a set of routers that are interconnected by a set of communication links. And the internet's core operation is based on a principle known as packet switching, which is really relatively simple. The idea is the following. What happens is that the end hosts that we talked about earlier take application level messages, divide those messages into chunks of data, put those chunks of data inside packets, and send those packets into the internet. Now, those packets are then forwarded along a path from a source node to a destination node. For example, from a web server, maybe to your laptop that's running a web browser that made a request from that web server. So let's unpack that last statement just a little bit, because we actually heard a lot of important words here. We talked about forwarding. We talked about a path from source to destination, and we talked about a source and a destination. There are two key functions performed inside the network core: forwarding, sometimes also known as switching, and routing. Let's take a look inside a router so we can see what these functions are. Forwarding is a local action. It's about moving an arriving packet from the router's input link to the appropriate router output link. Forwarding is controlled by a forwarding table that we see here, and there's a forwarding table inside each and every of the millions of routers in the internet. When a packet arrives, the router will look inside the packet for a destination address and then look up the destination address in its forwarding table, as we see here, and then transmit that incoming packet on the output link that leads to that destination. Well, that's pretty simple conceptually, lookup and forwarding. But you might be wondering, well, how are the contents of that forwarding table created in the first place? And that's where we encounter the second key function of the network core, and that's routing. Routing is the global action of determining the source to destination paths taken by packets. As we'll see, routing algorithms compute these paths and compute the local per router forwarding tables needed to realize this end-to-end forwarding path. A good analogy for understanding the difference between forwarding and routing is to think about taking a trip in a car. I recently drove from San Jose, California, all the way to the East Coast to Northampton, Massachusetts. It was a long trip. Well, I decided to take this upper route here rather than this lower route here. And that's the routing decision that's made, the path that's taken from the source, San Jose, California, to the destination, Northampton, Massachusetts. Now, when I get to an interchange, say in Sacramento, California, I'm coming into the city on one of the input roads, and I need to be forwarded out of the city on an output road. In Cleveland, here, and really at all intersections along the way. That switching from an input road to an output road is the local forwarding function, with the global routing function determining which of the output roads I'm actually forwarded onto. You might want to think just a bit about this relationship between the local forwarding function and the global routing function. Can you think of other analogies? Let's next focus on the transmission of packet bits at a router in the network core. In this figure here, we're illustrating the bits in a packet being transmitted from one router to the next. You'll hopefully recall that we said that if a packet's L bits long and the link transmission rate is R bits per second, that it's going to take L divided by R seconds to transmit the packet into the link. Transmitted bits will be received and gathered up at the receiving end of a link until the full packet has been received. You can see the bits in the packets being gathered up here. Once the packet's been fully received, it can then be forwarded on to the next hop, and so on. This is what's known as the store and forward operation of a packet switch network. Now let's take a closer look at what happens as packet arrive to a router for forwarding. In this figure here, we see a router with 3 links. Let's assume that host A is sending packets to host C, and host B is sending packets to host E. And now let's take a close look at the input link rates. The transmission rate R of the link from A to the first hop router is 100 megabits per second, as is the second link from B to the first hop router. But the transmission rate of the link from the first hop router to the second hop router is only 1.5 megabits per second. It's almost 100 times slower. And this isn't far from the case in a home network, where the home network router may have attached Ethernets in the home running at a gigabit per second or Wi-Fi at 54 megabits per second, but the access link to the cable head-end is much slower, perhaps only 5 or 10 megabits per second. And so here's the question. What happens as packets arrive to this first hop router? Well, the router in this example can only transmit at 1.5 megabits per second, and certainly packets can arrive a lot faster than 1.5 megabits per second if A and B are both transmitting a lot of packets at the same time. If too many packets arrive at too fast a rate, then a queue of packets will form in that first hop router, as shown in the figure. Queuing happens whenever work arrives faster than some service facility can actually serve that work. And of course, we're all familiar with queues. Here's a queue of cars waiting to get service at the toll booth. We wait in lines in stores, at the checkout counter, and I imagine many of you have been waiting at lines in the bursar's office to pay your bills. Here's a group of people queuing to get in the building, and here's a group of folks in the UK waiting. If you've been in the UK, you probably know that queuing is actually the word that Brits use to say when you're waiting in line. The Brits are really good at queuing. Check out this video.
This is the awfully thorough guide to being British. Governor, call blimey. In this episode, queuing. If queuing were an Olympic event, then Great Britain would win gold. Then it'd wait for an hour, take a ticket, and win silver and bronze. No one queues better than the British. And if you want to fit in, you need to know the rules.
This is your brain when you're struggling to focus. And this is your brain when you're in the zone. But
Well, to get back to networking, packet queues are going to form at a router's outbound link whenever the arrival rate in bits per second on the input link exceeds the transmission rate, bits per second, of that output link for some period of time. When there are packet queues, they're going to be queuing delays. Packets are going to have to wait in routers rather than being forwarded on their way to their destination. And because there's only so much memory to store queued packets in a router, if the queue becomes too long and a router's memory is exhausted, an arriving packet may arrive to a router and find no memory in which to be stored. In such cases, a packet's going to be dropped or lost at that router. And as we'll see, the fact that packets can be delayed and or lost is going to be a major source of headaches for a lot of network protocols. Well, so far we've been talking about packet switching, and we've just seen that packet queuing delays and packet loss can happen because the network doesn't always control senders carefully enough to ensure that large queuing delays and packet loss doesn't happen. Now, packet switching is not the only way to build a network, and indeed, long before the internet was around and long before packet switching, telephone networks employed a different form of technology known as circuit switching. Let's take a look at circuit switching. In circuit switching, there's a notion of a call rather than a notion of packets that flow from source to destination. Before a call starts, all of the resources within the network that are going to be needed for that call are allocated to that call from source to destination. So once the call begins, the call will have reserved enough transmission capacity for itself to ensure that queuing will never occur. There's no delay other than propagation delay and no loss of data within the network because link capacity has been reserved for the exclusive use of this call. In this diagram here, each link has 4 circuits. The call from the top left to the bottom right is allocated the second circuit on the top link and the first circuit on the right link. The circuits are dedicated resources. They're not shared with any other users. It's really like there's a wire from source to destination. So all this sounds pretty good. No delays, no loss. Doesn't get any better than that. Until you start to think about the fact that since resources are reserved for the exclusive use of a call, but the circuits can go idle if there's no data to send on that call. And there's the rub. If the bandwidth isn't used by the call, it's lost. No one else, no other calls can use it. And so a circuit switch network can be inefficient, as we'll see in a second. Circuit switching is done in one of two ways, either frequency division multiplexing, FDM, or time division multiplexing, TDM. In FDM, the electromagnetic or optical spectrum is divided into narrow frequency bands, and each call is allocated one of those narrow bands and can transmit at the full rate allowed by that band. In TDM, time is divided into slots, and each call is allocated a periodic set of slots. The source can transmit only during its allocated time slots, but can do so at the higher maximum rate of that wider frequency band. So now that we've been introduced to the notion of both circuit switching and packet switching, let's take a look at a numerical example to look at the numbers of users that are supportable in a specific networking scenario. Here's a scenario we want to look at. Let's assume that we've got a gigabit per second link. There are n users, and each of these n users behaves as follows. When they have data to send, they need to send at 100 megabits per second. That's 1/10 of the overall link bandwidth. However, users are only going to be busy 10% of the time. That means 90% of the time they have no data to send. Let's take a look at a numerical example about how many packet switched users and how many circuit switch users can be supported in this network setting.
I know time is almost there, but I still want you guys to pay really close attention to this because this is very important. Okay, get this one, we're aware that this is really, really important. Talk about the conclusion is there, right? Internet is based on what? Packet switching or circuit switching? Packet switching. So the question is why, right? Here are the answers. Okay, make sense? Next one. Okay.
Suppose that n is 35 users. For the case of circuit switching, the calculation is easy. Each user needs 100 megabits per second under circuit switching, and so a circuit switch network can support at most 10 users at a time. Now let's take a look at packet switching. Remember, each user needs 100 megabits per second, so we can support 10 packet switch users, just like we can support 10 circuit switch users, no problem. But remember, each user is only busy 10% of the time. What happens if we allow all 35 users into the system? What's the probability that more than 10 of these are active at a given time? With more than 10 active users, that's the only time queues are going to form and grow. One can show with some basic probability and combinatorics, which are not required for this class, and so we won't go into this calculation here, that the fraction of time that more than 10 of the 35 users are active is 0.0004. That is, if we let all 35 users into the system under packet switching, then the percentage of time when queues will start to grow is less than 4/100ths of 1% of the time. That's a pretty small number. Maybe we're willing to put up with some very occasional delay and loss in order to allow all 35 rather than just 10 users into the system. This performance gain under packet switching is known as the statistical multiplexing gain of packet switching, and it was a key argument for using packet switching when packet switching was invented 60 years ago. Well, it may seem to you now that packet switching is just about the best thing since sliced bread. Is it a slam dunk winner? It might seem so, and even today's telephone networks actually carry data in packets these days. So in some sense, we could declare packet switching the winner. Packet switching is particularly great for bursty data when a source only occasionally has data to send. It's simple, there's no call setup, there's no resource reservation. A host just starts sending data that it has to send. We've seen that congestion, packet delay and loss can happen, but we'll also see that internet protocols, TCP in particular, will react to congestion by decreasing the sender's sending rate in the face of congestion. So congestion and loss can, in some sense, be avoided or at least mitigated. Is it possible to provide circuit-like behavior with packet switching? Well, as the saying goes, it's complicated, but we'll study various techniques that try to be as circuit-like as possible. Well, let's wrap up our introduction to the network core by coming back to a phrase that I've mentioned a couple of times when I've said the internet is a network of networks. What does that really mean, and how is that actually reflected in the structure of the internet?
So let's say you have to read an
Okay, I will stop here. I hope the videos are really available there, right? Please finish watch this part of video and really think about what's the difference of packet switch and circuit switching. Make sense? Remember, that is one of the key questions regarding to the Internet's foundation. Okay? Then remember, so far we talked about the delay, right? What a delay we hardly mentioned. Transmission delay. And another delay we mentioned is what?
Propagation.
Queuing delay, right? Also, think we will finish watching this, we also have other delays. Make sense? At least watch this one. Okay, make sense? Okay, thank you guys. See you next Monday.
Thank you. This is already uploaded. One slide. Is it already uploaded?
Yeah, the other slide is already